Hello and good afternoon, everyone. We are about to start the second and last session on challenges and opportunities in an era of smart cyber-physical systems. And this will be a direct continuation of what we had yesterday, the first session. And I would like to start with a little bit of introduction and recap. And then, as we said yesterday, we talked about cyber-physical systems, and we were getting to the challenge of how to deal with their complexity. And that's the topic for this session. So time is now 1 minute past, and we were supposed to start sharp, so let's get started. And by the way, we will use the same procedure as yesterday. So there will be polls, Q&A sessions. Please post questions. You're most welcome to do so. And we will have a leg stretch at 2 p.m. Central European Time. Okay, so let's start. I would actually like to restart by doing the same poll that we started with yesterday as a kind of recap, and just to see if by any chance you're voting the same yesterday as you did today. So you should by now be able to see the poll, and I encourage you very much to go ahead and answer. So for the newcomers, we are, as a recap, we are voting on the same vote as yesterday. What do you think represents a cyber-physical system? What answer would be mostly representative in your view? Let's see if we can get a few more answers. We have 66% answers so far. Okay, this is a recap. So, okay, a few more coming in. Great, now we are almost at 75%. And then let's have a look at the answers. And I do recall that there is a difference here. If you remember from yesterday, also yesterday we had this option with integrations of computation, networking, and physical process was winning. That corresponds to the first definition of CPS. So that's very adequate. Yesterday, we did not have much of this umbrella term. It came out quite low, and I'm glad to see we have some votes here. And that's pretty much what I presented yesterday. You can have different views of CPS, and there are certainly not one single correct answer. Cyber also means feedback, and it can be seen as an umbrella, and it certainly represents this integration. And you might also say, well, of course, it's also a clever term, perhaps from some point of view. So thank you very much. I think this was a nice evolution. Oh, I didn't share the results. I'm sorry. I was speaking about the results without sharing them. But now you see them here. So in the integration, winning, and I think we had more answers on the umbrella term compared to yesterday. Great. So let's move on. What did we talk about yesterday? Well, we talked about cyber physical systems, cyber representing feedback / computer-based systems integrated with communication and physical systems. We already have them basically everywhere in terms of embedded systems, in terms of cloud centers in different domains, and we are adding edge computing, and we are entering an era where this would really be omnipresent. And we talked about automated driving as a representative example of what's going on with automation, services, connectivity, electrification. We have this unprecedented open world environments, essentially releasing the robots free. We have a complexity here which will be inherited in the systems we are building and also represented by the organizations. We talked about the lag or the delay. These systems are cyber-physical. It will take time before they are mature enough. They have an impact. We talked about this X-by-wire. Legislation is here. Infrastructure has to be adapted. It affects many things. And as opposed to just pure IT-based systems, it does take a longer time. But we also said that when we have CPS platforms in place, innovation can come faster. We talked about this as socio-technical shifts, the classical S-curves, how new technology emerges, and the fact that we have multiple technologies. It's not just a single innovation. And that there are many characteristics, and one of them is the technological is the disruption that we may see here illustrated by Kodak, that once was leading cameras, the camera market, and now is no longer in business. We also talked about another facet that new technologies means new risks, and of course opportunities, and here manifested by a gold rush, very strong market drivers. And of course these market drivers, since they are so strong, they also cause some concern, because there is a risk that we will introduce systems that are potentially too complex, where there are unknown risks like cybersecurity threats, where there are unknown and unintended consequences. So here we will come back to that, but we need to sort of balance innovation and gambling versus dealing with the risks that are at hand. Okay, and a few more words. Well, I think I've stated this already. We also talked about the importance of using and leveraging and deploying the cyber-physical systems to deal with sustainability, including the circular economy, and to do that we need to manage the complexity, and that is the topic of today. So talking about complexity, first of all, we need to sort of share a view on what we mean by complexity, and I would therefore like to start out with the poll here, using some common interpretations of complexity. And again here, please select what you find most relevant, one answer, what you think characterizes complexity mostly in your view for cyber-physical systems. So let's see if I can start the right poll. It should be launching now. So you're welcome, and please go ahead and answer what you think, in your view, is most hard to deal with, perhaps. We will come back to that. You can interpret this in different ways, but you can think of it as what you might think is most hard to deal with. So we have 50% answers already. That's good. Almost 60% now. Just a few more, perhaps. Interesting to see that we have a few that doesn't have. Okay, now we got a few more words. Okay, we're almost at 70%. Any final votes? Do them now. And I will then close the vote now. And let's have a look at the results. So you should by now hopefully see the results, and if you don't, let me spell them out. So we had a clear winner, very clear winner, combinations of the above as a winner, and second place was heterogeneity. And then we had a few votes on basically the others. And so we will have now a look at these examples of these, what I would call complexity facets. And I think it's pretty clear that different CPS or different systems in general might have an emphasis on different aspects of complexity, as I think we touched upon yesterday also. But in general, I very much agree with you that if we have a really complex systems, it tends to have combinations of these. So let's move on, thank you, and have a look at these complexity facets. This one I was actually meaning to hide, so apologies for that, because I don't want to overrun, I want to keep the time. So first of all, in this session, when looking at complexity, we will use kind of a framework or a structure that looks like this. And I will provide the reference later on to this one. But essentially, the framework here that we've been looking at is that we are building a system, a CPS. It is developed by and managed by organizations, and it's acting in an environment. So these are, let's say, the kind of systems we're dealing with in a broader sense. We are building the system. Our organization will be also a complex system. The environment will be a complex system. And each of these will have complexity facets that we had in the poll just now. Typically, they can have size-related complexity, heterogeneity, behavior-related, structural-related, change-related, and so on. So we will now first have a look at complexity, these complexity facets, and we will in particular also look at the difference in the complexity facets between the cyber side on one hand and the physical side on the other hand. And then before moving on to the how we deal with complexity, we will be looking at what I call organizational limitations here, meaning really what are our capabilities and limits as humans, as organizations, supported by computers to deal with these complexity facets. So basically, we start here, complexity facets, move on to the limitations, and then go on to how we deal with complexity. One further aspect I won't touch upon, but which is kind of interesting, when we talk about these complexity facets, we can, for example, if we talk about lines of code, that's a common metric, a crude metric, but common in software engineering. That's what we might call an objective metric of complexity. We can measure that, and we could presumably also agree that that is a metric. Whether we agree that it's actually relevant is another thing, but we could agree on it. On this side, we have what we might call subjective complexity. Humans, we, teams, organizations will perceive complexity depending on our current situation, knowledge. So here we have subjective complexity. And we need to, essentially this also conveys that we need to deal with both sides, the objective and the subjective complexity. Okay, so let's have a look at following up on the poll on some of these. This will not be exhaustive, but some examples of complexity facets and some particularly interesting ones. And here are the ones we had, and let's move on. I'll just have a coffee sip. So first of all, when we build systems and look at traditional design methodology, you might be interested in looking at the book by Ullman, there is this well-known design process paradox and or phenomena. And when we build traditional systems, when we build a bridge or a car, an existing car or an aircraft, then we have over the years created a lot of knowledge that we are leveraging. And basically, before we release the systems, we have pretty good coverage about what will happen. Because if it is an existing system, it will have failed. We have learned over time, like the exploding steam engines we talked about, for example. So traditionally, this will be pretty high up, close to 100%. And traditionally, we will have means to do maintenance and so on, but we will basically have close many degrees of freedom. This is, let's say, the classical setting. And the paradox, I guess, is that these are really going in different directions. So we will have very little uncertainty here. Now, for the systems we have been talking about, we are, as we said, we are releasing them based essentially in much more open environments. Things can happen, unintended traffic construction, a spider on the window, a fire in a tunnel, things that we haven't thought about and that could have an impact on our cyber physical system, both on the physical and the cyber side. And when we build a system, there is existing knowledge that we may not have access to, that we may have understood. We will have a lot of assumptions, and we will have more unknowns. And this is not new, but it's essentially a growing scope with the more open environments. And we can talk then about statistical uncertainty, which is well known, like, for example, random hardware failures and failure rates for pieces of hardware. And we could also talk about epistemic or knowledge uncertainty, lack of knowledge. And what does this mean? It means that we would talk about an increasing cone of uncertainty. And this comes back then to this paradox that we had before. And what's happening here is that because we have more unknowns, we will be moving the red curve down. There will be a gap up to 100%. And partly, I guess, because we want to deal with that gap, we might be able to upgrade our system. We will be keeping the design degrees of freedom. And we might also want to do that because we want to have a better position on the market. So there are two trends here, really, that less design knowledge when we release the system, more unknowns, and at the same time, more degrees of freedom still left, meaning an increasing cone of uncertainty. And what does that mean? Well, it means that obviously we have more uncertainty. We need to be prepared to deal with that. And that sort of is a prelude to the means for dealing with the complexity that we will come back to later. But one direction here is to build systems which are more resilient, more robust towards unknowns, if that's possible. But you can think about standard techniques from fault tolerance, for example. Triple modular redundancy gives you certain kind of robustness, and although that's in a kind of it assumes a fault model, and that may have limitations in those open environments. But so this is one aspect, and the other aspect is to try to increase the degrees of freedom, such as being able to upgrade the systems, because this is something we need to do to deal with the inherent uncertainty. Okay, so that's one facet, the facet of uncertainty. Another facet has to do with that CPS are hybrid systems. And we had an example yesterday where we talked about feedback systems, and there was a graph of a feedback control system for a motor. And clearly, I think you are aware of this, but when we are building, also we had the example of the automotive development where we have mechanical components governed by physical laws, continuous time systems that we may approximate by linear systems. So we have continuous time dynamics on the one hand, and then we have discrete dynamics on the other hand. And the typical example of that would be a gearbox, where we go from one state, one transfer function, to an entirely different transfer function. And of course, the whole cyber part of the system with state machines and Boolean logic is discrete in nature at that level of abstraction. And essentially this means that we need to close these gaps. We need to reason about those systems. And as we will see later on, a continuous time system can be very complex on its own because the linear system is an approximation. And the discrete state space can be very complex. And then if we create models, these are approximations, and we have an exponential state space, which is an approximation, and that makes it difficult to for example, verify these systems. So that's on the behavioral side. But there are more aspects related to the behavioral side. So when we do these models, we have assumptions. And one key assumption that has been put forward in particular in cyber physical systems is the difficulty of combining these types of models, these models of computation. And Edward Lee from UC Berkeley has been strongly emphasizing the fact that when we have these models and compose them, it is kind of remarkable that on the digital side, we have very weak notions of timing. This is an example of C code for programming classical foreground, background embedded system. We have a main task, a main program running, and then we have an interrupt routine. And this interrupt routine will be triggered by hardware interrupts that we set up a timer. And this will have an intricate timing behavior when running, but we don't have this notion of timing. We don't know how long time this will take, what load the processor will have. So that means that we actually, when we aggregate these models, we will be lacking essential information, and it's hard to determine what will happen. And then further on, when we implement these systems, we have these models. Software is a model. We implement it on hardware, where we have electrons sloshing through the hardware, and all interesting things can happen. So we know very well that software is complex. We talked about yesterday about 500,000 lines of code, and in an Atlas Copco nut runner. By the way, I had a quick interaction with Atlas Copco, and it is likely, as we said, that most of those lines of code, 500,000 lines of code in the professional nut runner, are indeed related to the software platform and libraries. But in any case, we see that large amounts of software, large amounts of documents, we will have errors in them. And you can see industry average 15 to 50 errors per 1,000 lines of code. Safety critical systems, rigorously developed, still have bugs. Waiting to be triggered very rarely, and typically related to unknowns or unforeseen circumstances or violated assumptions. And then we have the electrons, and as I think many of you are from the electronic design automation domain, this is not new to you, but it's still very relevant. And with the shrinking sizes, single event updates, sets, radiation causing bits, zeros, to be flipped to ones, or vice versa, caused by high energetic particles, is becoming more of a challenge, not only in space and in aircraft, but also also on the ground. So not only do we have complex behavior at the model level, at the theory level, there are gaps in reconciling these theories, and when we implement them, we have additional effects. And then in addition, we have cybersecurity. So even if we have, let's say, worked very hard on the nominal functionality, on failing hardware and software, and done our safety practices, for example, this is not really helping so much unless we have considered security. And as we know, there are different facets of security. Traditionally, we would talk about confidentiality, integrity, and availability. There are many properties and different ways in which the operation of a system could be compromised. So that could be, if we have a service, for example, braking in a car, the system might be hacked such that that service is no longer available, or in a way that that service is available but not performing in the right way. We had the example yesterday of unintended acceleration of cars that has happened. That was because of, most likely because of faulty software and hardware design, and not because of cybersecurity attack, but that could also be the effect of a security attack. And then if the system services are not corrupted in that way, they could be corrupted in this way, but people may also get access to your service. We had the example of Stuxnet, the security hack on nuclear power plants in Iran, where it was possible to actually control how these certain devices used in the preparation of the materials for the power plant were corrupted and used in the wrong way. So it's sort of related here, but here these were actually controlled externally. And then we have data. So the integrity and the confidentiality. Data may be, data may be corrupted, leading to wrong services, but things may also be stolen. And data may be stolen, and confidential data may be accessed. And this is not new, of course, but it is really an issue now with the increasing connectivity. Here's an example from a modern car, where we have all kinds of connectivity, physical connectivity, wireless activity. We have a much larger attack space. We have much more open source software in the future cyber physical systems. That's another way of attacking these systems. And it's enough with one weak link, and that weak link may be technology or humans. Okay, moving on to structural complexity. We talked about the evolution of cars, an old car, a modern car. In systems engineering, there's a common representation of structural complexity, the so-called design structure matrix. And here's a depiction of the old car, a pre-1970s car, and the modern car. And you can see here on the design structure matrix, a simplified view of the components of a car. For example, the engine is connected to the clutch. The clutch is connected to the transmission, transmission to the differential, differential to the wheel, the powertrain. We have a connection from the engine driving the wheels. And this is symmetric because we have bidirectional physical forces. This is an old car that was kind of easy to understand. And it's pretty classical that this is symmetric. A modern car, on the other hand, each component here, as we saw yesterday, is programmable. It has a computer. So not only do we have the mechanical X connections, we also have programmable connections. Essentially, all connections are now programmable as well. One example of that is a modern car with the steering. Steering can still go through the wheels, steering affecting the wheels. But in a modern car, you will also have a vehicle stability control system. We talked about a little bit about electronic stability programs, vehicle stability control yesterday. So a modern car will have a system that senses what the driver wants to do. It senses what the car is actually doing, whether it's skidding on the road, for example. And if there is a deviation, individual torque will be applied to the right brake through this channel here in order to compensate for the skidding so that the car can follow the intent of the driver. And that's an active safety system that saves lives. But you can see here in a nutshell the structural complexity in that we get lots of opportunities to do things, but at the same time, we need new responsibilities, new components, there are new interactions, new things that can go wrong, new responsibilities. So this is an aspect of structural complexity. And continuing that thread, it is not only that we have these direct interactions, we now looked at direct interactions. So for example, vehicles steering affecting the braking. We have lots of full-blown errors here, direct interactions. But we also have a lot of indirect interactions. For example, software components controlling a mechanical system will make assumptions about the speed or the inertia. They will make assumptions about the mechanical system. And with the software, we have had those assumptions before, but with the growing amount of software, we will have much more of these implicit interactions. So I will come back to a few examples of that. So this really means that we do not only have interfaces, we have these assumptions. And that means that if we change something somewhere, we may have a difficulty, a problem somewhere else. One way to look at that is through the organization. So, of course, we have different disciplines. They have to understand each other. Here again, illustrated with the physical, let's say, mechanical engineer and the software engineer. They use different languages. But even more so, when we build modern cyber-physical systems, we have many people, many experts, many disciplines. In a modern car, I'm told there are 1,000 people developing a car today. With an automated connected car tomorrow, that will just grow to a much larger figure. So what does this mean with the interfaces and interactions? It means that, well, cyber-physical systems, as you have seen, are typically integrated systems. That means that, for example, if we introduce a new sensor, let's say a front sensor to detect obstacles, okay, so let's say we have some engineers working on sensing, we want a new sensor. Well, to do that, we will actually affect the mechanical design. The design engineers may not be so happy. We will have to work closely with them. It affects the design. It will also affect, of course, software, electronics. Sensors have a direct impact on controls, which should be somewhere here. It will have to be communicated. So typically this means that we make a change somewhere, it will have impact in other places. So systems filled with interfaces and interactions. There are a lot of mechanisms to deal with this, what we might call, what I usually call integration pasta here. And partially these techniques relates to the means to deal with the complexity. So we will come back to them. And this also means that we have concurrent engineering. So we have people here working with sensors, software, electronics. They work in parallel. They somehow need to manage this impact. And we are now coming to a sort of a complex figure, and we won't go into the details here, but I wanted to highlight just by going through an example here. So if we have a closed loop dynamic system, let's say the vehicle stability control or some other control functionality, then if you looked into dynamics or controls, then you know that the dynamics in this hybrid system will of course depend on the mechanical systems and sensors and on the control strategy. So we have these two things contributing to the dynamics. But as we saw, for example, through the slide, the emphasis made by Edward Lee on the timing, the actual execution of the software, the choice of processors will have an impact on the delays in this system, on the quantization, the discretization, and that will also affect the dynamics. So again, here we see the dependence that we make changes somewhere, it has impacts otherwhere, and that surely contributes to the complexity. And then sort of wrapping up, we have complexity which is really inherent, and then complexity which is not really necessary, but we may choose to have it because it is convenient. Maybe we are using legacy software, we are using an operating system. We won't be using all of it, but it's very practical to reuse it. It will be costly to redesign it, but this also means that we will have more software, more things in the system, more functions in the system than what we need. And in the software world, they talk about featureitis, and that is often related then to looking at IT systems that you add. There has been a tendency, and probably related to it's so easy with the software platforms to add more functions. And maybe these systems, or maybe for sure these systems have not always been developed so smartly with end users in mind, meaning that we have a lot of functionalities that are never used, meaning unnecessary complexity. So we now went through a couple of these facets of complexity, and before proceeding on that track, here we were sort of looking at complexity facets that could apply equally well to cyber or physical. Each of these could have complex dynamics or be heterogeneous. These facets could of course also apply to the environment, many different types of entities in the environment, entities that change, and to our organizations. But now let's look at what is really distinguishing here if we look at the cyber versus the physical. And this is partly summarizing a study I did during one of my more recent sabbaticals. And the idea here, there is also more to read here. We won't go through all, but some highlights. For me, this was a revelation. I think it is important. And perhaps to emphasize this, again, going back to the automotive as an example, with the change in many classical mechanical systems, we see much more software, and we see kind of a fight for struggle. And what will the mechanical engineers say? Well, when they will say, well, of course, there's a lot of knowledge there. Their systems are complex in one way. But the software guys would say, hey, we're the ones controlling the car now. We're the ones dominating. If we just have architects from the software domain, everything will be resolved. And of course, that's not true, because the complexity stems from the combination. And there are different types of complexity involved. So let's look at just a few examples here. In the physical domain, one of the key challenges is really that you have closely coupled physical phenomena. If you have a brake, for example, you want to control the brake, but then you also have where the brake will deteriorate, you will lose material, you will have pollution-related materials getting loose from the brake, which have an impact on the environment. Things can break, you have heat. All these are phenomena that are in the same order as the braking effect that you will have. And they are complex phenomena in their own right. On the software side, on the other hand, we have this state space complexity. And because of the connectivity, a little change here could potentially impact thousands of systems worldwide almost instantaneously. Here we have typically slower time constants. When we talk about machine learning, and in particular deep learning, we now have, in specific areas, superhuman performance. But on the other hand, as we know, we can't really reason about the robustness of these systems. So they may break suddenly and without warning. Another important aspect here, I think, without going into details, but we will talk about, I will come back to this basically, but as you know, in software, we have very powerful ways of constructing software. We have very strong foundations, the foundations for electronic design automation, compilation, and we can compile things and they will remarkably work when running as physical systems, preserving our abstractions of Boolean logic, for example. When we talk about physical systems, we don't have those powerful abstractions. Instead, we have multiple abstractions. So if we have like a behavior that we want to implement, let's say a mechanism that we want to move in a particular way, we could use multiple types of energy and actuators to make that happen. We have multiple platforms. And we simply don't have that transformational way. Right, this is very interesting, and for the interest of time, we cannot go through them all. I think an additional complexity here, challenge here is that for the software part, we tend to underestimate the costs. We tend to, it's hard to do these cost estimations upfront. We tend to underestimate maintenance of complex software systems. Okay, questions are most welcome on this, and we will come to a Q&A session shortly. And of course, what is really relevant here is that these are not only facets of complexity, they also represent the capabilities that we have. And when we put them together, we get these combined capabilities that we talked about before. And at the same time, we get the combination of their complexity. So, where are we? Well, we are ending up with CPS that are very complex, many facets of complexity, and that remarkably work most of the time. So I would just like to reflect a little bit on that, and I've been talking too lengthy now. So let's move on to another poll, and it's your time to think about. And of course, if you're haven't heard about this paradox, it's hard to answer, but still give it your best shot, and we will go through it. Oh, it seems maybe, I'm not sure if I forgot to share that before. Apologies in that case. But in any case, now let's move on to this poll. Poll number 6, and I'm launching the poll now, hoping and inviting you to answer. What is the meaning of the automation paradox? I see we have a bit more of participants now. Welcome to this session. For those joining lately, we are following up from yesterday and now dealing with the complexity of cyber-physical systems. So I realized we had some problems yesterday. Not all could see the poll, but hopefully you can still see my slide, and that's really the most important thing. The interesting thing is that this, as we will see, this paradox of automation, I don't remember the date, we will see it shortly. It was understood and formulated some 40 years ago. And even more interestingly, it's still very, very relevant. Okay, we have about 50% answers. Could we have a bit more maybe? Okay, thank you. We have 50%. And I'll then make an effort to, thank you, more answers coming in. I will stop the polling now and share the results. Thank you very much for answering. And for those of you that can't see, this was like a trick question, and there was a winning alternative. Number 1 was winning. And essentially, automation is clearly difficult for many tasks we as humans find easy. This is true, but this is not what is referred to as the automation paradox. The option here that you were choosing that came out as second, option number 3, is the right one. And we will have an example of that, but the paradox, it is really a paradox in the sense that the more we automate the system, you might think that, well, the more we automate, the easier things will be, but it's actually the opposite. And that's what's called the automation paradox. And let's have a look at that. So Lisanne Bainbridge formulated that almost 40 years ago in a paper I can very much recommend. So why did we have this question? I was saying, well, CPS appear to work remarkably well. And reflecting upon that, we could say, are they really working perfectly well? Let's discuss this for a while. So I'm doing this in the context of so-called safety assurance cases. If you work with the safety critical system, or sometimes with the security critical system, you have to make a safety or an assurance case. In safety critical systems, this is mandated essentially by any safety standard. The safety case is really a document, an argument that describes why people can trust this system. It's a compelling, comprehensible, and valid case that motivates and describes why someone could trust this system. And for example, it is applied for flying systems for aircraft. So here we have the example that I'm sure you have heard about, the Boeing 737 MCAS accidents, rather recent. If you haven't looked at that, I can really recommend that you do that. And this is really an example of that would correspond to automated vehicles level 3. So we have rather high levels of automation. The aircrafts can do a lot of things autonomously, but the pilot is still responsible. This is what characterizes a level 3 system. High level of automation, but the operator is responsible. And this is also a typical example of the automation paradox. So here we have highly automated systems. And what does that mean? It means two things. It means that because it is highly automated, the pilots are usually just sitting there doing nothing. They get less training. And when something happens, they have to step in. And the second point is that when something happens, when something goes wrong, this means that the automation has failed. Something, the designers didn't think about. Something potentially catastrophic has happened. it happens for people that are not engaged, that are not active all the time. So we are asking people to step into a system, into a situation where the automation doesn't make it. And now we are asking the people to do the job. This is the automation paradox. And that will stay at different levels. So even if we think that we have, let's say, a very highly automated system, let's say we remove the pilots, but we still have supervision of people remotely, and the situation remains. Or we just have people that have to deal with a HiPEAC automated system. So what does this mean? It means a lot of things. It means that safety and, let's say, dealing with complexity requires a constant struggle. This happened in one of the most mature domains, avionics, aircraft, with a very strong maturity, standards, procedures. But these were not obeyed. These were not followed. And that's why the socio-technical aspect is very important. Safety culture, the culture of the people involved is very important. Another aspect here, if we look at, for example, automotive domain, we talked about the unintended acceleration. You read all the time about recalls of automated vehicles. Sorry, about not yet, but partially automated. You read about recalls of vehicles. But there are many things that are closed in court. There are many things that you never hear about. So there's a lot of things going on that is hidden. So what does this mean? What it means that already today there is complexity, there are things happening. The things are of remarkable quality, but bad things are happening. And we are moving into a new range of complex systems where we need to deal with. We need to deal with the complexity. And that's basically now moving on in order how to deal with the complexity. But first of all, there are a couple of things we want to do. And so we, oh, right. Now I do remember there was a slide I missed. That's interesting. But no worries, we are in a dynamic situation, I think. So let's go back briefly and then come back to this one. So I think this works well. There's a little jump, I apologize for that, but you now understand that cyber-physical systems are complex. So we talked about all these facets of complexity, but for some reason, I skipped this slide. So what do we really mean by complexity? We can, of course, refer to these facets of complexity. We can have different metrics, like the lines of code. Kind of useful, simplistic notion is this one. The degree of difficulty in accurately predicting behavior. I think this is useful as a kind of intuitive way of talking about complexity, because if you think about the facets of complexity, what can contribute to this degree of difficulty? Well, all the facets that we talked about, right? The scale, the structural complexity, the behavioral complexity, the heterogeneity. So I think this works relatively well. But now let's move to another view of complexity, which I was just coming to. Thank you for your patience here. So this other view of complexity is the so-called Cynefin, I'm trying to pronounce that right, the Cynefin model, which comes from systems engineering. If you haven't looked at that, that's it. For me, there is one major takeaway of that, and the worldview of Cynefin is really that it says it's important that you know what kind of systems you are building. For example, if we are building a a cyber-physical system of today, I would say we are in the complicated domain. Let's say we take the MCAS, the Boeing 737. What does this mean? It means to build this system right, to get the right quality, to manage safety, reduce risks. We have methodologies in place. We have the practices in place. And indeed, one could argue that if Boeing and FAA, the avionics authority, had followed the standards, the procedures, etc., they would have managed to get this system right. But they tried to take some shortcuts. What's happening now, and what I'm arguing, is that these new systems, like automated driving systems, the cyber-physical systems of systems, we are really going into what Kuhn calls the complex domain, and that really means that we don't have methodologies out there. We need to create new methodologies, and that means that if you think that you are here, but you're building a system out here, then you may come up with very unpleasant surprises. Here you need to recognize that we need to learn. You need controlled testing. You need to learn what's happening. You need to learn the failure modes. Think about the exploding steam engines that happened once upon a time, or the failures of automated vehicles like the Uber accident and the Tesla accidents. We are in a new domain. We need control testing, we need new theories. That's basically the Kuhn view. So two different views of complexity here. And we are, in the next hour, going to delve in depth into the means. But before going there, I would like to go a bit into this organizational limitations. And we will start on that just before the break. So we have complexity. What does humans do to deal with that? And in a broad sense, I talk about humans, teams of humans supported by computer engineering systems here. So we have here a quote from Herman Koppens. I have a reference to a recent book by Herman that I also can really recommend. And what he is stating here is something that I think you intuitively very well understand, and which recent research into cognition really shows very well. That while we as humans have we have fantastic capabilities, but when dealing with these facets of complexity together, it's really hard for us to create a model that can deal with that. And we are going to have a look into some aspects of that. So looking at how the human body and brain works is extremely interesting. There is this classical rule of thumb that in our brain, we can only deal, in our consciousness, we can only deal with a limited number of things at the same time. Let's say 5 to 7, or Herbert Simon said 5 to 10 chunks. Beyond that, we can't deal with that in our short-term memory. We have a long-term memory, but if you think about the experts, each expert in, for example, automated vehicles, in machine learning or safety or mechanical components, they fill their long-term memory. There is no person that can fill all things that we need. And then we have a number of other interesting aspects here. You can think about humans as information processing systems. One can do analogies with hardware and software. I'll skip that in the interest of time, but essentially that would relate to the think fast, think slow by Kahneman. We have a very limited budget of attention, strongly related to the fact that we have this limited capacity of our short-term memory. So that means that we really need to keep track and work to focus our attention and deal with any potential interference. And then we think that we are rational beings, but if you read Kahneman and others, you will know that we use a lot of the fast system reacting intuitively, and that might be right, it might be wrong, there's a lot of biases involved here. There's also this interesting thing about the narrating self, that we have a way of experiencing things, but then our brain creates a story that may be different from what we actually experienced. So I think this would be a very good point in time to take a break. We will come back in 10 minutes to this, looking at some of the implications of this, in particular the boxing, and then we will come back to how we deal with complexity. So let's now take a break for 10 minutes. I will start basically 10 minutes past 2. Thank you so much for your attention so far. We will continue 10 past 2. Thank you. See you soon. Cheers. So I hope you are back. Welcome back. Time is now 10 past. I will start 11 past just to make sure everyone's back. I see I have one Q&A. Please do post questions. We will come to a Q&A session shortly, and any questions are welcome. Okay, time is now 11 past. Welcome back. So we had been talking about what complexity is, facets of complexity, different complexity of cyber versus physical side, and now also looking into human abilities and limitations. And just before the break, we had this view. You can think of a model of humans and the human decision making. And there are, as I mentioned, a lot of interesting things here. We will look in particular into this aspect of boxing, which is very important. But there are also other things here. You can see empirical investigations showing that we as humans have difficulties in dealing with systems which have feedback, indirect effects, and delays when things happen, not directly, but later on. But I guess the main focus I will be spending here is on the boxing. And this is apparently, if you read the book by Sapolsky called Behave, this is a feature we have in our brains. So we tend to deal with complexity by framing and narrowing. Oops, I'm sorry. And this is possibly needed, but it also means that it's hard for us in many times to think out of the box, to get out of our little boxes, these boxes that we construct. Think about scientific disciplines. They are arbitrary, they may have overlap, they may not be consistent. And there's also this aspect of groupthink, which even more emphasizes the boxing. If we are in the box, this means that we have a tendency to want to think like others think, and that makes it even harder to think out of the box. And just a few examples of that. We have already, I think, touched upon this boxing thing. I mean, we see it in the academic disciplines. One example I've studied in particular is some of the gaps between theories. And for example, in my PhD work, I looked at the gap between control theory and embedded real-time systems, and in particular scheduling. And there we have two theories that have shown prominence and have been useful, but they are not fully compatible. That gap has been filled partly over the years, but I think there is still a gap there in the way it is being generally taught and practiced. And just to give you one example here, so if you're into computer science and scheduling theory, those theories will talk about response time. Something happens, like an interrupt, an event, and you want the computer system to react. And you talk about the time from the event till the reaction. That's one notion of, let's say, a delay, which you can analyze. In control theory, you have a notion called the feedback delay. If you recall the delay from sensing to activation in a feedback loop, we had examples of feedback systems handled by computers. And it turns out that this may be the same, but it's not per definition the same thing. And that discrepancy can, of course, cause problems, and there's a need to clarify that and to reconcile the theories. Here, it's not, you will have to read the slides, but this is just another aspect of boxing where we see that I'm here talking about automated vehicles, and safety. And you can see here, all these are standards that are being created, that are evolving, that's happening now. Many of these are very new and not even established. And this just shows the complexity, of course, but also the boxing. There are different communities here. And if we think about, and there are more communities, there is traditional active safety, like the electronic stability control. That's not even covered here. There is passive safety, like building, protecting mechanical framework. These are other standards, other communities. So the boxing and this cognitive way that we humans deal with that makes it difficult, and we have to try to break out of those barriers. Yeah, there are so many examples. One more, just one more. We are creating a lot of data when we build our systems. In software engineering, they tend to talk, or they usually talk about application lifecycle management. In traditional mechanical engineering, they talk about product lifecycle management, keeping data, information, drawings, keeping software repositories, versions, and in different domains, you have different repositories. Again, that's an example of boxing, and it results in fragmentation because the data of a system, of a CPS, will be fragmented into different databases. That's a technical problem, but it's also a mental cognition problem. So now we can check off a little bit. We have looked at facets of complexity, more from the objective side, but also comparing cyber and physical. We have looked at that from the, partly at least, from the organizational aspect in terms of our capabilities and limits as humans. In addition, we are autonomous. We do not always do what we are told. There are communication barriers in different ways, partly because we have these different boxes, partly because we have different languages. And then we have the computer systems holding data and information. And they, of course, to be able to do anything, they need to have information formalized and captured. Then all information needs to be managed, and also the computer systems have interoperability barriers with respect to themselves and with respect to humans. And these objective and subjective aspects of complexity causes a lot of problems. And it's now time to move to how we can deal with them. And before we do that, let's take a little Q&A sum up before we go into the ways of dealing with complexity. I apologize again for that I missed to show the results of one poll. Do come back to me if you have questions. And in the question and answer, I only find one question by Jagannath, who says, aren't the assumptions of the legacy software utilized in IT systems skeptical, considering the complexity facets of CPS? I'm not sure I quite understand the question. Maybe, Jagannath, if you could elaborate your question a bit, we can come back to it in the next. We have one more Q&A session. Let's see, I talked about legacy software. Where did I do that? I remember, I guess I talked about that when I talked about the featureitis. But I'm not sure that is what you're referring to. But basically, just to recap a little bit, I think the main issue in the poll we had when talking about what are important facets of complexity, most of you agree that this is really the combination facets of complexity. And then we have the cyber complexity, software data, and the physical complexity, and it's really the combination of those. And what we have here, and perhaps what you are indicating, is that we have different types of IT or OT systems. We have embedded systems that are heterogeneous. We have communication systems, we have edge and fog, and we have cloud and IT. And that's also another dimension of integration and a way, another dimension of heterogeneity that makes life more difficult, introduces complexity. But do feel free to come back to me if I failed to respond to your question, and more questions are, as I said, most welcome. We have the last part here, the last module, and that module is divided into two parts. One part is about how do we deal with complexity today? What are our standard means of dealing with complexity? And the second part is really considering these new types of CPS. What might we need to do different? And we'll start that with Paul, I think. How do we currently manage complexity? And the floor is very shortly yours. Let's see if I can get the right poll running. It should be running now. So we talked about all facets of complexity. What is your take on how to deal with complexity? The list is not exhaustive for sure. Other would be relevant. And of course, normally it would be a combination, but you might here indicate what you think is the most important way of dealing with the complexity. So we have 48 participants, and so far 40% responses. Let's hold a little while more. You still have a chance to vote. I hope you see, right, maybe not all of you see the questions, but you can still think about them. We have 43% answers now. A few more maybe. 43% answers. Okay. Let's stop there then. And I will make sure to share. Excuse me. So the answers, and we have a winner. Your take on this was that divide and conquer is the best way. And then we have abstractions, and then embrace it and other. And yeah, what can I say? We will now look at how this is seen, and divide and, oh, by the way, there is maybe one thing I should point out here. It was interesting to note that there was no answer, actually no answer on alternative number 2. So no one felt that we should eliminate or reduce complexity. And I think that's kind of interesting, because many of the proponents, the people that have worked in complexity, they really emphasize, I think, the importance of the second option a lot. But then, as you have responded, divide and conquer is a very common technique. Using abstractions is another very common technique. And embracing it, well, it sort of relates to the others. But let's move on. So what are the techniques that we find used? I wanted to first show you a slide, and it's an old slide, but it relates to, if you go to industry, there is an old saying in industry, and I would say in systems engineering, how do you deal with complexity? And that experience then says that, well, we can deal with it in the technology by having, for example, a very strong architecture that facilitates integration. That's one way to deal with complexity. Another way could be to have these very well-defined processes, like think about the aircraft business, very well-defined processes, very well-defined safety procedures. If you follow them, you will be doing fine. And then another way is to have a very competent organization. And sort of the intuitive saying here is that that in the old days you could emphasize maybe one or two of these and you would be fine. But tomorrow, with the increasing complexity, you really need to emphasize all three of them. So how do we deal with complexity? Well, we will have a short walkthrough and overview. And obviously, you won't come far if you don't have the right people, if you don't use good practices and right knowledge and theory. But beyond that, these are the techniques that we will briefly have a look at. And you already responded to partitioning and abstractions. I think you're well aware of them. What you didn't respond to was the assess, eliminate, or reduce complexity. And another very interesting concept is that of new conceptualization. So let's have a look at that. Okay. Assess, eliminate, reduce complexity. Okay, so I wanted to give you a very short story that Bill Shepard told me. I had the opportunity to meet him a couple of times. He was the commander on the first crew on the International Space Station. And what did he talk about? He, among other things, he talked about the toilets on the International Space Station. And as you know, the International Space Station is a collaboration. The EU, the US and the Russians are collaborating. And then at the point, there was a promotion of different technologies. So the Russians had toilets and the Americans had toilets. It turned out that the American toilets were very sophisticated. They had lots of software and electronics. And the only problem was that they were very hard to serve up in space. The Russian toilets were simpler, easy to serve, they were modular. And guess which toilets are on the International Space Station today? They have Russian toilets. So there's also this statement here, and I guess it particularly relates to software. With software, it's all too easy to actually come up with things that are more complex than you really intended because you're building on so many other things like libraries and platforms. And what this lesson says here is that you have to make a trade-off. Do I really need that complexity? There's a cost-benefit trade-off that has to be made. And then there's the additional thing of the complexity that you might have hidden inside software, for example. And then we have the recent book by Herman Koppes that I mentioned that I can really recommend. And he has this term, simplicity is complex, which I think in essence means that to come up with a design which really gives you the qualities and features you need, but in a not unnecessarily complex way, is not trivial. In that sense, simplicity is complex. So this is important. And then we have dividing and conquering, and this is standard technique. So dividing into parts, and then you have interfaces separating them. What is important here, and that I will come back to, is that interfaces, this is kind of a well-known, it's very well-known in systems engineering that things tend to fail not because of the parts, but because of not well documented or managed interfaces. This is well known by experts in the field, but I feel that this may not be well known in general. And this is, as we talked about, interfaces in dependencies all over the place. This is becoming more and more important. Okay, we could also talk about dividing things into doing things. If we have the parts, we can deal with them concurrently. And then we have abstractions, essentially models or views of a system. So for example, we might look at reliability, or we might look at logic or functionality. And this is powerful, but again, we have to take care about the boxing, that we don't forget about the assumptions, about how these things relate to the things that we abstracted away. And there are different types of abstractions. So, for example, we talked about continuous time physical systems that we could approximate as linear systems. That's an approximation as an abstraction. We could also talk about aggregations. Think about an end-to-end delay in a distributed computer system. We could talk about the explicit delays of the computation here, communication here, software buffers, and what have you. Or we can aggregate that and say, here's an end-to-end delay that will emerge into an application. That's another type of abstraction. And then interfaces deserve special attention. Right, and just to elaborate a little bit on that, models are strongly related to abstraction, and models are really key in engineering. And if we use models in the right way, in particular, we find a way to abstract, to simplify, which we can verify and which is valid in a particular context. Model validation is really a key aspect here. Then these things can be very powerful. And to deal with models, of course, we need to pick a language, a formalism. We need to pick the right level of, or a good level of abstraction. We need to pick right useful tools. What we have to observe is that when we use models, we also have to manage them. We are creating many models. If you take a car, again, we talked about cars many times. You have many types of models, and these models will have to be managed. The models have different purposes. The models become systems in their own right. They have components, they have structures, they have versions, and they need to be validated. Right, and then there is an additional interesting insight that if you take a view of physical systems, you tend to look at the real world and create a model of it traditionally, and then you want a model that mimics the real world. You go from the real world to a model, and in doing, for example, automotive engineering, people spend a huge amount of efforts in doing that, because that would facilitate for them, for example, to do early verification, model in the loop, software in the loop, hardware in the loop simulation. And then you can say that if you have a difference in behavior, you would say that the model is wrong. You need to adapt the model to match the physical world. If you look on the cyber side, or perhaps a bit more on the CPS engineering side, you could instead think of a model as a blueprint, and you want to generate a cyber physical system. You want to generate code or real behavior in a software hardware system, or even 3D printing. Then you could say that, well, you have a model, you want to generate something, there is a discrepancy. What is wrong? Well, you might say then that it's actually not the model, it's actually the implementation. So slightly different facets of this. But models for sure belong to this facet of dividing and conquering. And then we have many models. And how do we deal with them? We have this integration pasta, a well-known way to resolve some of these dependencies, to look at emerging behaviors or unintended effects, is that of getting all the systems together early so you can simulate. And you can also do that using models and in an optimization setting. That's another way to focus on early integration. And then you can have other tools like having specific models that models these interactions. We had an example before of design structure matrices, the DSMs, if you remember the matrix of the components of a car. That's common in systems engineering. That's an example of a kind of an integration-specific view. And then you can also have multi-view frameworks, essentially defining multiple views and ideally also describing how they are dependent. And then if we have models and tools, well, we can do model exchange and synchronization. These techniques also have their pros and cons, but these are available largely today. They can for sure be improved, but they are available. Okay, and then we have this fascinating approach of new conceptualization. I think many people use this similarly as abstraction. So sometimes when you hear people talking about abstraction, they might actually mean new conceptualization. So what does this mean? Let's look at two examples here. So one example that you should be very familiar with, we have analog transistors. They are used to shuffle electrons, and we have voltages and currents. And we know that we are able to create a new concept, many new concepts. One of these new concepts is actually Boolean logic or instruction sets of processors. So this is actually an approach where we are going beyond what some people might call an ordinary abstraction. We are creating entirely new concepts that do not inherently exist at lower levels. Another example put forward by Herman Koppes is that if you have clock synchronization of normal clocks in a distributed computer system, then you have the normal clocks and you're creating, by use of some suitable clock synchronization mechanism, that is coordination between the clocks, between the nodes. You're creating, again, a new concept that is not existing at, let's say, the level of the single clocks. And then, according to this, and you can read more in the book by Herman Koppes, the distinction here is that, for example, if we talk about an end-to-end delay, well, delay is actually a concept that does exist at lower layers. We can talk about worst case execution time. That's really a delay. It's not a new concept. And then we can aggregate and represent it at the higher level. But if we have these kind of abstractions, new conceptualization, we are creating entirely new things. So I think this distinction, although perhaps theoretical in a sense, it's worthwhile because normal abstraction is useful and important, and this new conceptualization as kind of a stronger abstraction is indeed also extremely important in dealing with complexity. And here you just have a view of what's happening in the electronics world. So we have these different notions when we are going from physics to Boolean algebra, to instruction set architectures, creating new concepts. And that's really the what has, I think, enabled this tremendous progress in software engineering and electronics. So then we have dealt with how we deal with the complexity today, and we are now going to look at how this is dealt with tomorrow, or how we need to deal with it. Maybe we could just have a little stretch here. Okay, there was one question. Poll 7, what is the correct answer? Okay, let me go back. Just taking a little break. Poll 7, where were we? Okay, what is the correct answer? Okay, Yeah, so the answer provided by the participants was divide and conquer. And you were asking him, what is the correct answer? I'm not sure there is a correct answer. I think the correct answer, as we said, depending on what CPS you have, that CPS might emphasize different aspects of complexity. So the tools you use to combat complexity might be different. There might be different answers to your question. I think in general, the sensible answer, if you think about your engineering arsenal of techniques, would be that you need a combination of techniques. You may need to emphasize some of them more than the others. So, and then we were looking at what we are doing today. And now we will be, as a wrap up, the last 20 minutes, we will be looking at what we need to emphasize for tomorrow. More questions are welcome. Thank you. So essentially I have 5 pieces here, and this is just a memory map. As you know, we can only remember 5 things, and this is just to keep the thread. We will come back to the Kinevin model of complexity and to look at what does that really mean again with respect to new methodologies. Then in the beginning I mentioned I had the opportunity to be part of this Platforms for CPS study, and we had a special theme which was complexity management, and we will look at the results from that study. Then we have the complementary study I did during my sabbatical. We will look at the concept of resilience from socio-ecological systems and see what lessons can be learned from there. And then there will be a wrap-up synthesis. So, Kinevin, as you recall, making a distinction between the complicated domain to the complex domain. If we look back to automated vehicles and what we are seeing there, what does this mean? It means we don't have all the methodologies in place. We have to learn as we go. So we have to learn. So what do we need to do? Well, we need, obviously we need experimentation and we need test beds. These could be real physical test beds. They could be large scale, smaller scale simulations, of course. And we need that to learn more and to develop new theories and methods and tools. We also need, because we are lagging data, we are lacking information about how the systems can fail. We are lacking information about what could happen out there. This could be failures, of course. It could be hacks. It could just be interesting things happening on the streets. I remember there was an early Google video shot when they had one of their automated vehicles running in Silicon Valley, and it came across an old lady in a wheelchair chasing ducks. That is kind of an unexpected scenario, probably. The car managed, but we need to learn, we need to gather these things that can happen. And then we need forums for debate as well. But as you know, as we talked about, legislation is not there. What does safety mean for automated vehicles? Automated vehicles will run into accidents. They will, in effect, be part of killing people. But what is the level of risk we are willing to take for automated vehicles? Who will be responsible? So this is a takeaway from the Kinevin methodology. We need to learn. These are things we need to do. Then moving to the Platforms for CPS project, I do recommend the findings that are available openly online. I have that in, I have a list of references in the end. So then we had some work and some workshops referring to complexity of future cyber physical systems. In particular, we were also looking at existing practices such as systems engineering. And I haven't touched upon that explicitly, but as you may know, systems engineering evolved when dealing largely with complex physical systems, such as space travel, space shuttles. How do we manage the complexity? And there's a realization there also that current practices are not enough. So here are the findings, basically. I'll just list them here. We already mentioned environment, that because we are targeting open systems, we need to have we can't expect the requirements to be, they were never easy. They are not easier. They are much more difficult. What will happen out there? We have touched upon composability indirectly, at least. We talked about facets of complexity of cyber parts, physical parts. We need to reason about the combination of these, about the combination of components, about the combination of control theory, scheduling theory, machine learning. We have different theories, and we need to resolve. We would like really to have results that says, oh, I guarantee reliability, and that will not have an impact on, let's say, control performance or something else. Okay, complexity beyond our current capabilities. We have talked a lot about that. Then there was a lot of discussion, of course, different, whatever we mean by artificial intelligence, but perhaps in particular, machine learning, deep learning. We see all kinds of software algorithms, model-based, deep learning-based, going into these systems. That's a new ingredient, and we need to understand how they work, and we need to reason about their, not the least about their robustness. And then we have human CPS. So this is kind of frustrating in a sense. We have been interacting with complex systems for quite a while, and yet this gap that engineers tend to develop systems that are developed for engineers that are not so intuitive, this remains. It's not for sure only the fault of any specific discipline. It's difficult to get sociologists, psychologists, engineers to work together. And we need to emphasize that much more because these systems will be omnipresent. We want them to be understandable, predictable, robust. I wanted to give you one example here of that relates sort of to the environment and the composability here. This is an example from a study I and colleagues did a couple of years ago at KTH in Stockholm. And as I mentioned, as you know, we're working with automated vehicles. And so one strand of work is on modeling and simulation to evaluate architectures and safety for highly automated vehicles. And what this slide shows is a snapshot from a couple of years ago of modeling and simulation tools that were then proposed for simulating automated vehicles. And there are a couple of very interesting takeaways here. One takeaway is that this map is very volatile. New tools are emerging all the time. This is significant of the technical shift. There's a new market for tools. And there's learning available, new opportunities. So tools are appearing all the time. This is by no means complete. Another takeaway here is that each slice here represents, for example, we have sensor modeling or vehicle dynamics modeling, control modeling, control prototyping. Many of these slices represent mature areas. MATLAB Simulink, rapid prototyping, or vehicle dynamics has been around for quite some time. So many of these slices are mature. What is not mature is their combination. And that's really an example of this lack of methodologies. We have some pieces of the puzzle, we don't have the combination. There are also newer new pieces of the puzzles. For example, how do we model the environment, the scenarios? How do we reason about, how do we even think about coverage of such models? So there are new ingredients, and the main new ingredient is the combination. And to simulate these things, we typically need co-simulation. We need combinations. We need different co-simulation technologies. Right. And then, in the end, if you have these wonderful tools in place, the question still remains related to the methodology. When are we done with testing? So, new methodologies are needed. And here I would just like to follow up. This is basically a summary from work I did in 2018. And you can read more about this, and you recognize we have been talking about the facets of complexity, human limitations, and we have been talking a lot about these things. But I guess what so there's some overlap here, but what I want to emphasize here, or just underline again, we have talked about it, is that in the CPS, we have to look at both the cyber and physical side, but there's clearly much more software and data. So the complexity facets of these things need more attention in combination with the physical ones. And the interrelations to us, when we looked at this, really interrelations, interfaces, dependencies, really seemed like something that was not sufficiently well represented in current engineering methodologies. And just to give you one further example of that, some earlier work I did to address this, let's say the boxing, although we didn't really think about it, we weren't entirely aware of the human limitations, but we were just observing that we have more and more viewpoints, more and more disciplines, and they are acting, they are not independent. And we were saying, well, we really need ways to deal with these interactions. And then we came up with a couple of concepts to sort of reconcile these at different levels. The first level is, you might, and we coined it partly to talk about design contracts. So if you remember, we talked about the gap between control theory and scheduling theory. Well, if we have a contract, a kind of an explicit agreement, we could then explicitly state that this is what the control guys mean with a function, a state, and a delay. And this is what the computer scientists mean explicitly with functionality, states, and delays. And then we can actually, ideally, if we have that contract explicitly, these guys could understand then I can change this thing, the delay, a bit, because I might have tolerances. There's robustness. If I change within the scope, I can go on. If I change more, then I have to renegotiate. I have to meet with these guys. So that's the idea of the design contracts. And this can be generalized then to any set of contracts. And at the model level, you can try to capture the dependencies. You can think about linked data traceability, or more semantically rich links, which will tell you, I'm changing this, therefore I have to look into something else. And you can think of implementing tool support for that. So one of the last lessons learned here, when you look into cyber physical systems and sustainability, you find very interesting overlaps or underlaps. And one thing I discovered was this book and research in socio-ecological systems. So quite different from CPS. This deals with sustainability, let's say sustainable agriculture, what people do, and what we will do with crops and fertilization, for example. Or it could be other socio-ecological systems. It could be how we deal with water, clean water. But in any case, there are a couple of principles that have been formulated, apparently rather recently, and I really see a strong potential here to leverage and reconcile this. There's also, I think you will recognize many of the things I talked about. So, for example, when we build a robust CPS, well, we know from safety reliability that we will use redundancy. We may in some cases use diverse, redundant, and different types of designs, whether it's processors or algorithms. Connectivity we recognize. This is well known in this context also. Slow variables, feedbacks, something that the cognitive psychologist knows that people have difficulties in dealing with. I can also recommend that you have a look into an area which is called systems thinking. I believe I will come back to that. And this has to do with these systems that have many facets of complexity and they are changing. Learning, of course, the things are evolving. The systems are complex not only technologically, they are involving many stakeholders, lots of people. And in this sense, these people also look at our political systems, how we govern them. And essentially, as you can see, they are promoting certain principles here. And if you take them one step further, that would certainly lead in the direction of democratic systems as a way to build more resilient socio-ecological systems. So we have looked at different aspects here of complexity and human limitations. And I think some of the takeaways that I want to emphasize here is that we need design for X, design for equality, or design for sustainability, design for resilience. This has been there, but it's becoming much more important. Integrated design, co-design, whether we talk about humans and CPS, whether we talk about safety and security or different aspects of security, cyber and physical, there are more and more aspects that we need to take into consideration. That grows the scope, more people, but it's becoming more and more important. And that means that we need to try to leverage new techniques to learn more and develop new methodologies. And one very important avenue here, the human CPS, one way we can leverage new ways of dealing with complexity is really having humans to collaborate with computers. This is not new, computer-aided engineering, but we will have new opportunities here with AI assistance. And in particular, as we know, we humans are very good at certain things. We can deal with things that the computer systems cannot deal with today. And computer systems can today do things better than we. And these things tend to be different. And in particular, also, we need to leverage much more visualization here. Two other things is that, and as a takeaway for the PhD students in the audience, as you see, we are marching into these systems. That means that for you, technology, of course, will be important. In-depth knowledge will be important. But however you work, collaboration and communication skills will just get more and more important. And these are extremely challenging, or another way to phrase it is that even if you're good at it, you can definitely become better. And this is a skill worth investing in. And finally here, I think that it's important for the things I've talked about to be aware, to increase awareness of the objective and the subjective aspects of complexity that we talked about. So how do we deal with complexity? Maybe coming back to what you said, Kim, in your question, I think combinations is the key. We have of course, it's very important to eliminate complexity. I think a new ingredient or an ingredient that needs more emphasis is to look at design for X, that's looking at the co-engineering between different involving multiple disciplines and over the life cycle. And because the systems will fail because we are learning, we need to more strongly emphasize resilience and changeability. And we are building risk metrics into the systems. We have to understand the complexity of environments. We need to deploy monitoring increasingly in these systems. And when it comes to managing complexity, dividing and conquering and new conceptualization are still important. We need to come up with new ways of doing the partitioning, abstraction, and conceptualization. And changeability has very much to do with quick iterations. And as I mentioned, we have to support humans in doing all that. So as I'm now getting to a couple of wrap-up slides, and I hope you have energy for a few more. So wrapping up the whole story, we said that we need to leverage CPS to really use them to serve mankind, to get human-centered systems, to deal with sustainability, and to do that, we need new methodologies and we need better understanding of complexity. And then you might ask, which I have been alluding to, what can different actors do? And this is more, let's say, to emphasize this, but these things are very important, and we can see various initiatives, and I can only encourage you to engage in these. And these are initiatives we can take as individuals, as in organizations, or at the, let's say, legislation or policy, governmental level. I think with the pandemic, there is a window of opportunity that we should try to do the most to leverage, and doing that at different levels. And then there is a difficulty in balancing innovation and risk that I also have been touching upon. If you go to Arizona, certain places, or if you go to Silicon Valley, Palo Alto, you will find yourself immersed in an environment with a lot of level 3 automated cars, with people trying out their automated vehicles, and there will be test people watching the steering wheel, and that means that you are suddenly in a more risky environment. If there's a failure in the automated vehicle and the test driver is not awake, which happened with the Uber accident, for example, there may be accidents. So there is an example where there's a particular point of view emphasizing innovation, perhaps, rather than risk. In Europe, you see slightly more emphasis on the risk aspect, and it's an open question, really, what is the right approach here. But what is clear that we need to learn more. When it comes to education, many of you are into education. We are talking about CPS as a socio-technical shift. This also means that education needs to renew. Why does it need to renew? We still need the basic skills. This is right. But we need to look holistically at education. We cannot put everything into education, but and we really want people to learn a lot. So that means that lifelong learning is really, we can't learn everything. We need to continue to learn. So one renewal is to sort of embrace and promote and support lifelong learning. Another type of renewal has to do with what we call T-shaping. So we need experts that can solve machine learning, safety, security, what have you. But these engineers also need to collaborate. So they need not only the expertise, the deep knowledge, they need a breadth in knowledge. They need to be able to collaborate. This is the T-shape. And we need to rethink that T-shape. And just to give you one example, right now at KTH, we are developing a new course in cybersecurity and safety. There are very few of these courses available, and we can just say that in many universities, you find that at one end, you have computer scientists. They may learn a bit about security, but typically very, very little about safety and very little about physical systems. And at the same time, embedded systems, mechanical engineers are likely to learn about safety, but not about security. So this is just an example. Then we are in a very strange, or maybe I should say interesting world, where education often has low status. Research has high priority. Promoting and actually embarking on this renewal doesn't have high status, it's not promoted. So we have a problem at the universities in trying to reverse that. And I think that this needs actions from a lot of stakeholders, but surely universities and industry can act proactively in doing so. And if you're interested in that, you might be interested in looking at competence networks, where we have in the Stockholm region working proactively to promote this industry together with academia. So what is KTH doing to deal with the challenges I have mentioned? Well, KTH is very big, and I am not represented. I can't represent the whole of KTH. We have 350 professors. That also mirrors the increasing scope of competence and kind of the gaps. These professors do not always speak together with each other. We have 5 schools and we have many more departments. But essentially, as I mentioned, in this competence network, the ACACES competence network, we are promoting educational renewal in collaboration with industry, recognizing that there are different types of competence. So in academia, we will be very good at the academic or the scientific theories, but there will be knowledge out there which may not always be captured in terms of these theories. For example, systems engineering dealing with the life cycle of a very complex cyber-physical system. That knowledge tends to be in industry and not in academia. Test beds for CPS, I mentioned that, and that's something we are promoting. There is a test bed for smart homes. We are establishing a larger scale test bed in intelligent transportation, building on an existing 5G installation at KTH, digitalization of the campus, and our own automated vehicle. I did mention the IRIS initiative on sustainable industry and society. We have the new Teckosa Center. And here if you're interested, you're very welcome to come back to me. We have lots of opportunities for collaboration in various ways here. So with these words, I would like to wrap up. And I would like to thank you for your attention. I hope you have found this expose interesting. We started with automated vehicles, generalized to cyber-physical systems as a socio-technical revolution. We looked at the interpretations of CPS, characterizing them, different aspects of different types of CPS, and the need to leverage CPS for sustainability, and in order to do that, the need to deal with complexity. And as I mentioned, we are talking with CPS about digitalization in the physical world. There is a lot of emphasis on the digital and the cyber aspects, and this is for sure something that is happening, and it means that innovation goes faster. But it is important to remember that cyber-physical systems are indeed also physical. These things are integrated and become new systems. And therefore, we have to look at the integration of these systems, including with humans. And innovation, as I I hope I have shared, can of course come in different parts, like in the cyber part, the physical part. It can come in terms of business models. So we can have innovations in different parts or at different levels of CPS. And with the increasing scale of CPS, the question becomes, how can we trust these systems? The automation paradox that we talked about is more relevant than ever. And wrapping up, we started with this picture, increasingly complex systems capabilities. We need to manage the complexity, deal with sustainability, and be aware of and somehow try to manage ourselves. So with these words, there are plenty of interesting directions, and well, it's a wonderful world. Plenty of research challenges out there. I have mentioned many of these things, and I have reference here for reading. The first two are part of the complexity study I mentioned, and then I mentioned the integrating viewpoints, and then we have other sources of inspiration. And with these words, I would like to open a final Q&A session. There is still some time for wrap up. And let's see. Okay, yeah, I don't have any more questions apparently. So if there are any final questions, please feel to post them now, or feel free to come back to me later. I enjoyed these two sessions. It was valuable for me. I hope you have enjoyed them. And as I said, you're welcome to come back to me for questions. I would like to thank the organizers for their summer school and for being brave enough to go about having an online summer school. Thank you for your attention.